guys. Today I want to talk about how physics is often misrepresented or misused in modern cinema, or even just films that, dates back to when it even just started. So first example, we're going to take a look at John Wick 1, which is honestly one of the best action series, in my opinion. So we're going to look at a scene where John, the main character, breaks a glass pane by just throwing a body onto it. Let's take a look at this clip. You can see he threw this guy over the window and it broke immediately, like it's like candy or something, right? Um, okay, so let's first take a look at the mechanical properties of glass in order to see how this is actually a misrepresentation. So the compressive strength of glass, which basically is how much force it can take without breaking per unit area, right? So for a typical pane of glass that's used in a household, right, it's 1,000 newtons per millimeter squared, or in terms of pressure, it's 1,000 millipascals, right? So just take that in mind. So it takes 1,000 newtons force if that force is concentrated over, you know, a, a square millimeter. And so, what is the throwing force of a human? So there was an experiment that talked about throwing washing machines, which actually are pretty similar to humans in weight, and it showed that basically an average man, like John Wick in the film, can exert a force of about 1,000 newton on an object around the weight of a human. So, well, we now know, right, that glass, we have to concentrate all of that force into just 1 square millimeter in order to break that glass. So for sure, we can't just break a pane of glass that big by throwing a human onto it, unless, they're wearing like a spike or something that's able to concentrate all that pressure onto that pane of glass. And in fact, I don't know if you heard of the experiment where, you have one single nail and you push a balloon onto it and it pops right away. But if you have like, say, 1,000 nails, concentrate it and you push a balloon onto it, it's not going to pop like with the same amount of force. And that's the thing with pressure, right? That's the same thing with glass. If you concentrate that force into a very small area, it's gonna, break more immediately because of the compressive strength, right? So there's a so basically as the contact area decreases, the pressure increases. And yeah, for things like glass, they break easily with higher pressure, right? So technically, if you have, like a very, 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 very infinitely small dot, you don't need much force to break a gigantic sheet of glass because the pressures are so strong. Okay, so now we can say John Wick 1 is now busted in terms of physics. Okay, now we're going to take a look at another John Wick film, John Wick 3 Parabellum. Um, so there's a scene where Sophia, just a character in the film, shoots John, and then with the pistol, right? And then it knocks him off his feet. So let's first take a look at the scene, right? Pretty interesting, pretty cool.
Sophia? Sophia!
And there it is.
Sophia?
Okay, so is that possible in real life? So first of all, I gotta say, John Wick, or played by Keanu Reeves, is wearing a technically impenetrable um, jacket in the film. So the bullet would not have gone through him. So we know that the bullet will be either lodged in him or have bounced off of him, and more likely it's lodged in him, right? So we're going to consider it as an inelastic collision where, two objects collide and then they stick to each other, right? And then now we can see, you can probably see where this is going. It's becoming a momentum problem, right? So momentum, right, is basically mass times velocity of an object, right? So let's first of all, let's look at the muzzle velocity of a bullet that they use, the 9 by 19 millimeter parabellum bullet, and it actually depends on the muzzle size and the barrel length, all that stuff, what kind of pistol you're using. But the average 9 millimeter bullet, which weighs in at about 7.45 grams, travels at 430 meters per second. That's the moment it exits the barrel of the gun, which I mean is going to decrease in with air assistant in real life. But we're just going to assume there's no energy lost, or there's no momentum loss to friction and all that stuff. So there's no deceleration in the bullet, basically. Um, okay, so with that, we can calculate the momentum of the bullet. Okay, so what about the weight of Keanu Reeves or John Wick? Right, he weighs in at 175 pounds, which is 79.4 kilograms. Right, and now we know the mass of the two objects. We know the initial velocity, and so now we can calculate the final velocity, knowing that they would combine together. Right. So as I said, assuming a perfect world where momentum is conserved and the bullet doesn't break off, meaning that it doesn't bounce off or break into multiple pieces and then some of the pieces gets off, some pieces doesn't get off. Right. It's just easier to calculate. And also, this would be the case where it transfers all of its momentum into John Wick's character, into his body. Right. If imagine if the bullet breaks off or it bounces off or it keeps on traveling, some of that momentum might be, um, transferred into or remained in the other parts of the bullet. So we're just going to assume that momentum is an elastic collision where they stick together. So now we can do the calculations, right? We can use the equation, right? The initial mass times the initial velocity equals the final mass times the final velocity. Now we know the initial mass, initial velocity, and the final mass, which is a combination of Keanu Reeves and the bullet, which, I mean, in this case, really the bullet is quite insignificant compared to such a large mass. I mean, it's what, in the thousandth place compared to the kilograms, right? So, anyhow, we're still going to consider it. So, as you can see, if we do the calculations, we end up with 0.0403 meters per second, right? That's the final velocity if they were to move together after the collision. And that is very slow, right? That is not even walking speed. So definitely it wouldn't knock you off at your feet. But still, we're just looking at it at a sort of basic standpoint, just to sort of get into this idea of using momentum and how we can actually apply simple physics in real life. So yeah, now we can say John Wick 3 is sort of busted as well. All right, so here's an interesting one. This is a childhood classic, Superman from 1973. I'm sure many of you guys have seen this. I certainly remember this scene from my childhood where Superman flies opposite of the Earth's spin and reverses time, and he saves everybody's life, saves everything from happening. So let's take a look at that scene first. Yeah, so you can see, he flew opposite as yeah, he flew opposite of the Earth's spin right here. And then suddenly everything sort of reverses itself, right? We're gonna say time just reversed because the dam seemed to magically repair itself. The cars got out of the ground seemingly, opposite of what happened just moments ago, right? Um, so to talk about if this is realistic and to sort of chip in at a not so complicated and more intuitive angle, let's first talk about um, two very important things of physics. That is consistency and symmetry. So what is consistency? Well, the consistency of physics basically is that the laws of physics are always consistent no matter where you are, right? So in any physics described, there's always an observer, right? When you're talking about when we were just talking about the bullet and hitting John Wick, right? We were an observer standing in the room, right? So the bullet and John Wick is moving relative to us, right? And but we as an observer is not moving relative to the earth or the house that's beneath us, right? So just sort of wanting you guys to know the idea of having an observer. And so basically, right, as I said, consistency is the laws are basically always the same, right? When you apply force to an object, no matter where you are, no matter if you're on Earth, you're on Mars, it's always going to be the same. You know, when you apply force, it's always going to accelerate an object with mass. So that's consistency. Now symmetry. Now this one's more interesting, right? So basically it says the laws of physics are always consistent no matter when the observation is made. So this might be less intuitive because we can't really travel back in time, but well, a better way to think about it is that, if you throw a ball right now into the sky, it's gonna fall down. But if you throw that ball, say like a month later, it's still gonna be the same, right? The physics are not gonna change about it just because time has changed. So let's say, we have a ball that's at rest, just at when t is at some time, right? It's at rest, in the sky. Obviously, gravity is pulling it down, right? So we know it's going to accelerate downwards, right? So as you can see from these pictures, right, the ball is slowly accelerating downwards. And right now we're seeing, time is moving from the left to the right. However, if we say reverse the time, so if we go back to this picture, now we're looking at from the right to the left. So we essentially reverse the direction of time. Still, gravity is still causing the object to accelerate because now it's not accelerating towards the Earth, it's actually decelerating, right? So it's slowing down to rest. Right. And in the first, so now it's starting with a velocity and it's going to zero velocity. And still, the only force applied to it is still gravity and it's still causing it to accelerate just the same, at negative 9.8 meters per second, assuming we are on Earth, of course. Um, so yeah, no matter what direction of time you have and what where in time you are, the laws of physics are still the same, right? And that's very interesting is that, you know, um, basically it means if we reverse time, we wouldn't be able to tell it just based on the laws of physics, right? But that seems kind of weird, right? Because if we think about it, that's not how really time works, right? Like if a dog runs on a beach forward, right, and you record a video of it and you just sort of reverse that video, right? You're obviously going to know that that dog is running backwards. That's not how it works, right? Unless it's a very weird dog. So this only works for the laws of physics, but if we were to reverse time, we can still tell that time is reversed, which is why, when we saw the clip of the film, you could see that time was reversed, right? At least that's what it was trying to say, right? We saw the dam repair itself. We saw the car get out of the ground, although everything was indeed still obeying the laws of physics. So, what is a better way for telling time, right? If we can really tell the direction of time with simply physics, well, we can't just say, this looks normal to me, right? Because that's not very scientific, I wouldn't say. So now we're diving into this thing called thermodynamics, right? And that is a lot of things, but essentially it contains this concept of entropy. And entropy, some say, is a measure of chaosness, right? But I'd say a better definition is the number of ways to arrange particles in a set system, right? So, and that might be a lot to take in for now, but let's take a look at these graphs. Right, so on the left here, we have this system, or just whatever's in this box, of multiple particles, right? We have the red and the blues, right? And now they're sort of, bunched up together, right? And when particles are closer together, we say they're solid or liquid, right? And um, when they're solid or liquids, because the particles can't move as much relative to each other, there are less ways to organize them such that they're still a liquid, right? Because if you pull the particles super far away, they're going to be a gas, right? So basically, yeah. And on the right side here, we got like a bunch of messy particles that's, just floating around, bouncing around as a gas, right? And now the particles can be essentially anywhere in this chamber, So there's now basically infinitely more ways to arrange them such that they're a gas. So now they have a higher entropy, right? And a classic example to explain this is, think about your room, right? When you clean it up, right? It's less messy. There's less ways um, for the things to exist, right? Because your books are, on the bookshelves. Your pencils are in your drawers, right? Your clothes are in your drawers, um, you know, and all these stuff. There's less ways for you to take all these stuff to for these stuff to just go into places in your room. So there's less way to arrange them. Um, However, if your room was to be like super messy, everything is just out and about, right? There are now much more ways to get those things around, right? This razor can be on the desk, it can be on the bed, it can be, on the ground, the clothes can be, just hanging on a shelf or something like that. But anyhow, I hope you can see that there's now more ways to arrange these objects in the system that is your room. So now it has a higher entropy. So yeah, hopefully now you understand the basic concept of entropy, that it is a measurement of chaosness or the number of ways that things can be arranged in a system. Now, the second law of thermodynamics says basically that the entropy of the universe always increases. And if we think about it, it sort of makes sense, right? So obviously solids, because the particles are so bunched up together, have a lower entropy than, say, a gas, because the gas particles just roaming about, right? And that's what we see is that things, solids tend to melt, right? Things tends to go from a state of low entropy to a state of high entropy, from solid to gas, from liquid to gas, from solid to liquid, right? Yeah, so that's basically what this law is saying, this trend that is how entropy works, basically. And right, that got us thinking, right? If entropy always increases, that has a direction, right? Isn't that a better way for us to tell time, right? Like if entropy always increases, if we look at a moment in time and compare it to another, whichever one has a higher entropy in the universe has, is obviously going to be a later time in time, right? And the one with a lower entropy is going to be earlier time, right? Um, which is why it's often noted that as the arrow of time. However, I'm telling you that this is not always true. So, a redefined or more well-defined um, second law of thermodynamics is that the entropy of a closed system sometimes increases. So it doesn't always increase, but it sometimes increases. Actually, in most of the times it increases, right? So notice how I didn't say universe, right? And we're going to dive into that later, but just take that in. It doesn't always increases. If we're just looking at this box right here, right? It doesn't always increases. And why is that? Let's take a look at this box here. There are 9 particles, right? In each of these boxes, and they're the same box. They're just in different positions in time, right? So on this box on the left here, we have a solid, obviously, right? A state of low entropy. And on the box in the left, we have the same 9 particles, but they're, much farther away in a higher state of entropy. The question is, which direction is time flowing in this closed system, right? If you knew about the second law of thermodynamics I just talked about, entropy always increases in the universe as time increases, right? You would say that time is flowing from the left to the right, right? Um, so that the box on the right must be a captured, in a later time than the box on the left. However, that may not be true, right? And why is that? It's because of randomness. And that's a big idea you're gonna see, especially in thermodynamics. It's just that a lot of things in our universe is based out of randomness. And so if we look at this, right, I am now claiming that time is flowing from the right to the left. And why is that? So let's take a look at this, right? Say that we have the box on the right here, right? And that started first. What if, say, each of these particles have a initial velocity that's moving towards each other, as you can see by these gray arrows, right? They're moving towards each other, right? So they're bunching up together. So as time goes on, they're going to move closer and closer and closer until they start to attract each other, and then eventually they become the solid that is depicted, by the left, on the left. So wait, so we just went from a higher entropy state into a lower entropy state. Whoa, that is weird, isn't it? How the assortment the of your initial velocities for these particles can essentially affect how entropy is decided. So, are we still saying that entropy is a good measure of the direction of time if this can happen? Like, if like didn't we just say that entropy always increases? Like why would that be true if everything can just flow together? Well, that's why I said that you know entropy only sometimes increases in a closed system, because if we think about it, there's billions of billions and billions and billions and billions, an almost infinite amount of particles in our universe. And what is the likelihood that they all come together suddenly, right? Without, actually forming some actual issues like a black hole or something becoming too dense. But just think about it. What is the actual probability that all of the particles just suddenly all had a you know, velocity going bunched up together, right? And is that even possible, right? If we think about it, now everything is moving in just a random direction, but things seem to collide with each other to change the directions. So when you collide with a thing, right, typically they go in opposite directions, right? And that means they can't really go together, right? So it's very, very, very extremely unlikely that entropy decreases as a whole on the scale of the universe. So sure, maybe in this like very minute, very tiny, space, sure, maybe two particles bunch up together and entropy just suddenly decreased by a very, very small amount for a little bit. But it doesn't mean that on the whole scale of the universe, we are, you know, having this gigantic decrease in entropy. So, right, basically each singular molecule have to point simultaneously at the same direction for an extended period of time while colliding with each other to have a total decrease in entropy, which is basically impossible, statistically speaking. Right, so this is saying that, basically entropy is always going to increase as time goes on in the universe, right? And hopefully, I hope you can see that, our universe is really amazing in how it's arranged in randomness, right? How these things are really decided by the random nature of things, right? There's more likelihood for entropy to increase and to decrease. So entropy increases in the universe. So yeah, very fascinating, at least to me. So, right, now let's sort of recap what we just said. So we've concluded that entropy is definitely going to increase in the universe, right? And we now know what the definition of entropy is, right? So let's think about the things that we saw in the film, right? The dam just broke, right? And it apparently went back into itself, right? So that is going to be a decrease in entropy, right? Because when the dam broke, it broke into more pieces, right? And think about it, it's like a solid, right? And it sort of became like a gas, right? It was a bunch of particles bunched up together where they can't really move relative to each other, and then they, sort of became an arrangement of particles where they can move relative to each other. There was only one piece of dam, and after it broke, there's like what now 1,000 pieces of dam. So obviously entropy increased. Um, it increased when the dam broke, right? And in the film, we saw, the dam sort of just went back into itself, right? And that is now a decrease in entropy, and we know for sure that that is not going to happen, right? That is not going to happen. Um, because even though it might work out physically, we still don't really have a scientific method of changing the direction of time, and we know that the because the laws of physics is consistent, entropy is always going to increase, right? Um, so it's impossible that the dam will fix itself unless, I guess, unless you're Superman, which um, it's kind of magical, but still, we don't really have a method into reversing time, or else we'd be, advancing so much in history right now. But unfortunately, we don't know how to reverse time. We don't even know if it's possible, and I don't think it is because of entropy and all the limitations we just talked about, right? And also, if you think about it, what is time? Because isn't time just defined by man, right? So you can think about those questions. Those are very interesting questions. And I hope, you know, it sparked some interest in you in the realms of, thermodynamics or time or theoretical physics or chemistry. Anyhow, just a little interesting fact here. Um, if Superman did spun the Earth backwards, it will probably also kill every person on Earth, because of the wind. And if you want to look into that, you should look into this wonderful book written by XKCD. Um, it's called, I think it's called How To. Yeah, How To. And there's an arrangement of different interesting scientific problems, which hopefully you can dive into and sort of, you know, uh, divulge yourself into, explore your interest in there. But yeah, hopefully this video has been pretty interesting to you. And obviously Superman is busted, fortunately. So yeah, if you want to look into these sources, you can feel free to check them. But yeah, hopefully you've enjoyed this video, and yeah, hopefully you can continue becoming a more scientific person in improving your knowledge in our wonderful universe um, that is given to us. All right, so hopefully you like this video. Be sure to give it a like, and if you want, subscribe to our channel. All right, have a blessed day. See ya.